So, Barb and all of you, thank you for joining tonight. It's a pleasure and an honor to speak to you. Sorry it's not in person, but I'm happy to at least have this opportunity remotely. Hopefully you'll be in person at some point soon. So, fun time to be talking about these topics I'll be covering tonight. Interesting time in the world, interesting time of the year, obviously. So, going to be focusing on bird migration and specifically some of the lessons that we've learned as part of the BirdCast project's approximately 20-year history now. Some perspectives on what it's like to think about monitoring and learning about migration in the 21st century with new technologies and also some old technologies and integrating the two things. So hopefully many of you have now experienced BirdCast one way or another. Just to take it all the way back to the beginning. So currently BirdCast has three main partners that are really leading the science, soon to be four. Cornell, the UMass Amherst, and Colorado State, and soon to be University of Illinois, Urbana-Champaign. And this group of collaborators is really the union of ornithologists and computer scientists that had, as a sort of a rare opportunity, about 13 years ago, we received an NSF grant, an award that really kicked off the version of the BirdCast project that you see today, which is all about automating the analysis of radar data, forecasting, and observing bird migration on radar, talking about it, relating it to what we see on the ground, really showcasing the spectacle of migration. But there's another 10 years before that that really are critical for the evolution of BirdCast that date back to the early 1990s. Excuse me, to the late 1990s, to 1998, 1999. And the Academy plays an enormous role, an important role in that. They were one of the founding partners in the first BirdCast project, along with Cornell and Clemson, where I was at the time, National Audubon, and also a company called Geomarine, which really does sort of consulting and radar work for industry and various others. So there's a pretty long history of BirdCast, and it goes right back to the Academy. Frank Gill, Sally Conan, I'm sure some of you remember and know. It's pretty amazing to be able to talk about it from the perspective of where we are now and where we've come over that 20 plus years. So let me get into it a little bit. I probably don't have to tell all of you about nocturnal migration, but I always like to sort of think about this slide because one of the primary ideas behind BirdCast is capturing the spectacle of migration. Of course, most of that happens at night. So we know that, of the world's birds, at least 20%, that's probably a very, very conservative number. It's probably quite a lot more than that, are migratory. And we know that in North America, maybe 7 out of every 10 birds, it might be a little bit higher than that, depending, are migratory. And of those, we're talking about 4 out of every 5 migrating at night. And even that might be a little conservative. Turns out there are a lot of birds that move at night that we are just learning even now after, at this point, a century and a half of very solid ornithological work, even more in the United States. So suffice it to say that there's a great diversity of birds that move at night, and capturing that information, of course, is extremely challenging because it's extremely rare that we can see what's happening at night. Now, certainly some of you hopefully have had the experience of watching the moon at night with a full moon and using a telescope trained on the moon and actually seeing birds fly across. This is a wonderful photograph from a colleague and friend of ours who's a sort of a new friend who emailed us out of the blue and said, "Oh, I have this wonderful setup that I take pictures of the moon, and sometimes birds contaminate my shots." So I said, "Okay, we can deal with that. Like, just send those all to us." So this is obviously a multiple exposures, but I mean, it's a wonderful image and captures the concept of moon watching very well. And moon watching was one of the first ways that we really started to understand the magnitude of the migration that was happening at night. And in particular, some of the work really in the late 1940s, 50s, and early 60s that was promoted by George Lowry, Robert Newman in Louisiana, and continent-wide surveys of people watching the moon for numbers of nights during the fall. The first really kind of continental view of how extensive and how intense is nocturnal migration over really broad areas. Obviously, it's highly limited to use the moon to study this. Identification is hard. Yes, there are those among us that can probably pick out what those species are in this image by silhouette. And yeah, you can do a few maybe, but you run up against a limit pretty fast, of course, of being certain about what the IDs are. And of course, you also run up against the limit of needing a full moon and also needing a clear view of the full moon. So not the most ideal way to reliably study what's happening at night. Fast forward to the evolution of new technologies. Think about the early part of the 20th century and all of the advances happening in electrical engineering and physics. And one of those advances, or a series of those advances, related to this notion of using microwave energy, pulses of electromagnetic radiation, to survey the atmosphere. That you send it out, send a pulse out, it strikes some things in the atmosphere, and it comes back to the antenna. And you can localize where these, in quote, targets are, whatever they are, and you can have some sense of how many there are, maybe in what direction they're moving and in what speed. A very powerful way of surveying the atmosphere. And as it turned out, the evolution of this technology, which of course was radar, had very integral in its discovery and its application the use of birds to study its efficacy. So in two different ways. One is obviously testing it against something that's flying in the atmosphere. Birds obviously represent a really easy, in quotes, target to see. And second, that the radar operators, in particular those that were starting to employ radar technology at the beginning of World War II, we're starting to see these really odd patterns. On the right-hand side of the screen, you'll see what one of the images captured from the radar screen looks like. Very different from what we see today, but still indicative of a pattern. In particular, there's hopefully you can maybe see the mouse here. There's sort of a very jagged, very bright white pattern here that's classified as angels. And those angels are birds. Of course, at the time, many people didn't know what these things were because they didn't employ enough birders to do the checking and the quality control and the ground truthing. But once they did, they realized that these are birds. And in fact, pigeons and starlings represented a pretty significant number of the early detections by radar. But the concept has been there of using radar to study birds flying in the atmosphere for now about 80 years or even a little bit longer. So it's a long-standing opportunity to think about, oh, how might we surveil the atmosphere in places where we can't easily see? And radar offers us a really excellent opportunity. So fast forward a few more years, post-World War II, there was also the realization, of course, that not only were the radars very good at detecting enemy aircraft, obviously, and birds, but also weather of all different types. And so during the 1950s, this military application of radar became the civilian and commercial application of radar and the meteorological application. And a network of radars was deployed across the United States over the next 40 years. As early as about 1955 were some of the first ones. And this kind of give you a sense of what the coverage was. They did not all become operational at once. Really, the first ones were along the Gulf Coast with the idea that they could provide an early warning system for inbound hurricanes, of course, not to study birds, but to study weather, in particular extreme weather. But nonetheless, it evolved into a network, and quite an extensive one, even by the mid to late 1970s, that operated into the early 90s. Come that period, we get the next generation. Some of you may have heard of NEXRAD, Next Generation Radar, or WSR-88D, which is Weather Surveillance Radar 88 Doppler. That is really the second or third version of the weather surveillance radars that we have in the United States. And as you can see, the coverage is a little bit more. There are 143 of these around the contiguous US. There also are some in other places in Alaska and Puerto Rico and in Korea and parts of the Pacific. But the coverage is greater. The technology is quite a bit more advanced, in particular, the ability to identify what speed and direction targets like precipitation or birds or bats or whatever you might have is moving relative to the radar. So a major advance from the first network. And of course, also the digitization of the data. The first network was all recording data on film. And now in the 1990s, by the late 1990s, we're talking about digital data. So a really unique opportunity when we think about what these radars can detect in the atmosphere, which is all sorts of amazing activity. So here's an example of some of the radar data. Should look familiar to you if you've seen BirdCast or if you've watched the Weather Channel or probably local news. What you see here is a mosaic of the 143 radars around the US, in particular from May 15th. And you'll notice a few very strikingly different patterns here. There's a very blocky, irregular pattern, the bright yellows and reds that you see, particular in the Great Plains, but also in the Great Lakes here. That represents precipitation, basically occurring at boundaries between air masses. So where you might draw, if you were a meteorologist, a frontal boundary between warm and cold air. And then there's another pattern that you see here, which is the much more uniform stippled blues and greens, almost sort of annular patterns that are a lot more uniform. And that's biological. So we have the meteorological on one hand, we have the biological on the other hand. And because of the specifications of this radar network, the biological signal is dominated by birds when they are present. So really what we can think about here is a situation where we have an image from all these 143 radars surveilling the atmosphere of meteorology and biology dominated by birds. And if we can identify what the meteorology is and understand what that is and remove it, suddenly we're talking about an incredible way of surveilling the atmosphere where we can quantify, characterize, hypothesis test, all sorts of amazing information about biology dominated by birds across the continent, and obviously down to the scale of each individual of these 143 radars. So potentially a really powerful way of thinking about all this movement that happens under the cover of darkness that we can't otherwise quantify easily. So the other amazing thing about this is because this is the National Weather Service under NOAA operating this, since its inception in the early 90s, all of the data are archived, they're freely available. And so there is this incredible and immense archive of give or take 500 million, 750 million radar scans that is available for use if you can find a way to dig into it. Now, that's a tall order. This is where BirdCast comes in. That was, in fact, one of our tall orders for the project, was to figure out, because computer scientists were interested in messy data and a lot of data and making predictions and understanding and characterizing quickly, and we were interested in understanding where and when birds are going to occur. This was a wonderful opportunity for collaboration to advance, let's say 15 years ago, what was the cutting edge of big data analytics, the first cloud computing ideas, the very origins of machine learning. And now, 15 years later, give or take, we have cloud computing as ubiquitous. We use it all the time, pretty much. We're obviously speaking, on a remote meeting at this point. I'm not with you per se, and all sorts of incredible machine learning tools that we hear about practically every day in the news that are incredibly powerful and incredibly good if you can train them with expert knowledge about, what's bird migration and what's meteorology. We filter out the meteorology, and then suddenly, wow, we have 500 million or 750 million images from which we can analyze and characterize bird migration. So we can do that now, which is just like the most amazing accomplishment, I think, from the project in many ways, is this ability to finally be able to say the number that I've wanted to know for my entire life. How many birds are migrating annually at night over the contiguous US? This is from a paper published 5 years ago, and the number is enormous. So we're talking about billions, of course. In the spring, the green arrows representing birds passing a transect in the southern US and a transect in the northern US, 2.5 to 3.5 billion birds. Of course, every summer, those birds are going to produce young. So in the fall, there are more birds. Those orange arrows passing those same transects representing 4 to 5 billion birds. So massive numbers of birds aloft over the United States on an annual basis. And now we can start to make these kinds of characterizations. And we can do so, as I mentioned, for all of these images. So not only do we have the potential of generating these kinds of annual flows and understanding for the first time, well, how many birds are there? How does that change over time? How does it vary across the United States? And maybe more importantly, once you have that, we have the capacity to try to predict where and when these movements are going to happen on radar and be able to build forecast models. And so that was one of the next steps, was relating all of these available data to us, those hundreds of millions of scans where we can train a machine learning model to recognize what's weather and what's birds, and then also then relate that in a model to let's say weather factors, for example, temperature, wind direction, speed, pressure, a whole variety of the weather data that you could characterize that is of interest to humans as much as it is to birds, and build a model that relates those forecast weather data to what we see on radar. And then suddenly, when you have the forecast weather with a nice model that behaves in a way that we can understand, that happens to behave very well and captures probably 80 or 85% of the migration variation that we see on radar based on just a few weather variables, then we have a powerful opportunity to create these kinds of forecast models. And this too, this image represents one of those types of forecast models that we publish on the BirdCast site. So hopefully it looks familiar to you guys. Probably looks very much like a weather map, where it's basically a sort of a heat map, an intensity map. The very bright colors, the whites in particular, represent areas of intense migration that we're predicting. And importantly, predicting 3 hours after local sunset, when migration tends to peak in the atmosphere, wherever you are in the contiguous US. And then, in addition, being able to think about the low end also. So where those purples and pinks are, low intensity migration. And understand that this represents not only where and when birds are going to occur, but we can quantify and make that prediction. So this is the forecast for tonight. It was going to be a big night, as usual, in the Great Plains, where an enormous amount of bird migration occurs in the US. Most of it happens in that area. And we're talking about a potentially really big night here. We'll see what happens, but talking about 500 million birds on the move tonight. And if that's not a big enough number, tomorrow is supposed to be even bigger. And this is kind of the prime time, as you all know, probably from your experiences in the field. End of September, beginning of October is really the peak period when you look at the entire continental US of when the largest numbers of birds align with the greatest diversity of birds. So big movements happening right now. And the capacity to forecast this is just a wonderful opportunity to leverage that machine learning that we can do and the available data to something that's of interest to the ornithologist. And frankly, when people see the numbers, even people that know nothing about birds are kind of captivated by this. And I think it helps that it looks a lot like a weather map as well. So not only can we do that, of course, the forecast, but we can then also do the near real-time characterization of, well, what's happening as we speak. This happens to be from last night. So just the concept here of taking those 143 radars, the green and red dots around the map here, and being able to analyze the data almost as soon as the radar collects them, about 10 to 15 minutes afterwards, we're able to publish the bird-dominated biology that those radars are detecting. So the incredible sort of the predicted map with the forecasts and the observed, if you will, with the near real-time radar data. So really wonderful opportunity to think about what we predict, how we do, and obviously where the birds are distributed. And of course, I also should highlight here that there are not birds everywhere across the United States. At this snapshot last night at 11:40 Eastern time, there are plenty of places where there are sort of the black areas of the eastern and south central US. Those are areas where birds are either not migrating because there is weather, or very small numbers of birds are migrating because conditions are adverse. So we really get a sense of sort of where these movements are. And when we dig a little deeper, obviously not from this imagery, but from additional analyses, we can really understand, well, how is weather playing a role in governing where, when, and how intense these movements are when they're occurring? We can also do some really fun things. That graphical approach, looking at the entire continent, is one sort of striking way of conveying where and when and how much bird migration is happening. We can also, of course, take advantage of the fact that each of these radars has really unique data as well. And so we can start to look down to the state and county level and present that information too. And in fact, present it in a rather different way. So rather than the graphical image of sort of the weather map type approach from the geographic background, let's think about a dashboard where we produce some of the metrics that we can extract from the radar data, the pattern of bird migration over the course of the night, the speed and direction of movement, the altitude that birds are flying. How does this night in particular relate to other nights of the season? Where do we stand in terms of a cumulative for whatever area, whatever county or state we're interested in? In this case, Cook County, Illinois. How many birds have passed over this year? How does it relate to the previous years? All that gray area in the background of the images you see here, that's all historical data for the last 10 years. So the green lines are trend lines for today or last night. The gray is background for historical information. So a really rich opportunity to convey what's happening at a much more local level. And of course, we also put in, even though the radar, I should say, is species agnostic. We cannot identify the species from radar. We do have eBird data. We have all those observations you're talking about at the beginning of the meeting, all the birding that you do, and all the data that you provide to eBird. We can understand what the species are that are on the move, and we report that as well. And so we sort of start to integrate those data sets. Now, part of the reason that, aside from that, we're really excited about this dashboard, which we unveiled last year, and the ability to talk about migration at an even finer scale than we ever have before. We also can think about this from another perspective. And I want to highlight a couple things. I know these are small. I can just sort of draw circles around them. And maybe if you squint your eyes, you can sort of see what I'm talking about. I'm going to talk about two areas of this graphic in particular, where we see the birds in flight over the course of the night. So you see sort of this hump pattern, right? And then also the altitude. So basically what I want to convey, in Cook County, Illinois last night, there was this really interesting pattern, which is pretty different from usual, where the bird migration numbers, the number of birds in flight, actually peaked later in the night, in the early morning. And interestingly, while that peak was building, the altitude of migration was decreasing. And
I had to
might imagine,
reinstall. Ugh.
as you might imagine,
Is that his slide?
that creates a sort of an interesting situation where we have real trouble. So some of you may have seen this. Last night and early this morning in Chicago, there was a major bird collision event. Some buildings reporting nearly 1,000 casualties, 33 species dominated by yellow-rumped and palm warblers. I know Philadelphia has had these instances before. Obviously, so has New York. So have many places. And the idea that we can now start to think about, how does migration play a role? How do different aspects of migration and birds interacting with different conditions, how does that play a role in these kinds of devastating and awful situations that we sometimes see, in fact, increasingly in urban areas? So one of the ways that we start to transition the science that we can do and the information that we can convey from the BirdCast project is to think about, well, let's employ that to really understand how might we make a difference in understanding about bird collisions. So many of you may have seen this graphic or at least heard about some of these numbers. So staggering numbers of birds die in collisions every year with various structures that we erect into the atmosphere. So for buildings alone, we're talking about the hundreds of millions up to 1 billion every year. Now, not all of those are migrants, but those collisions are, in fact, sort of equally distributed among very tall buildings like skyscrapers, glass facades on these things, and also residential homes, the same order of magnitude. So serious problem in terms of the numbers of birds that are killed. And obviously this relates to the altitude at which birds are moving, the numbers of birds, and of course the conditions in which they're moving. And of course, it also relates importantly to the fact that we have glass and reflective structures and that we have light pollution at night. So this bird window collision is a significant one, bird building collision. It's global. It's not just Philadelphia. It's not just Chicago or New York. It occurs in China. It occurs in Europe. It occurs all around the world, wherever we have built environment. And light is an enormous part of that. So let me just highlight a little bit here the issue of light. And you may recognize this as the tribute in light. This is the memorial to the lives lost on the September 11th attacks in 2001 in New York City and southern Manhattan. I've been very fortunate to spend time at this event for every one of the last 20 years as it's occurred. It is a powerful event. It has nothing to do at its core with birds. Of course, it is everything to do with psyche, emotion, a very powerful memorial to these lives lost, and many people that are still attending that are first responders or family members of those of the lives lost, or people that are just trying to support those people. One of the amazing things about this tribute, of course, which is extremely bright lights pointing skyward, as you can see in the left-hand image, to mirror what was there, the two twin towers. These bright lights, as do all lights, attract birds and they disorient them. So from very early on, it was clear that situations like this, where in this movie that you're seeing, this loop, this is approximately maybe about 2,500 warblers of primarily 4 species in the beams that you're seeing flying around right now. Looks sort of like snowflakes, looks like insects, all birds. There are some insects in there, but really what you're seeing here, dominated by birds. Ovenbird, black and white warbler, northern parula, and American redstart. And when the September 11th event, which is one night of the lights on all night, when that overlaps with intense migration, we see this attraction. And interestingly, we see this attraction in New York City, which is one of the most photo-polluted places on the planet, of course. So even in a place where there's enormous light pollution and birds are dealing with it, when you add more very bright light, birds are attracted even more to it. And the incredible draw of this, it seems that, yes, you can see these beams from on a clear night up to 100 kilometers away. It seems like it's at least attracting birds from as far as 10 kilometers away and as high as 4 to 5 kilometers above the ground. So this enormously powerful trap, if you will, if you think of moths to a flame or moths to a porch light, exactly what's happening here. We've been very fortunate to study this over the last 20 years, work closely with the organizers and producers to create this sort of situation where they will allow us to spend time studying it. They'll allow us access. They'll even allow us to tell them when dangerous situations like this occur, shut down the lights. And they will do it because they don't want to see any more mortality at the site. They don't want people feeling awful when they already do, any more so than they do, about a pile of dead birds at the bottom of the lights. Incredible win-win situation in terms of starting to work together to keep the tribute going and keep it alive, critically important, but also allow it to do so in a way that protects the birds that are passing. And just to give you a sense of what this looks like on radar, so that experience of being there, you can see it on radar even. And even though the radar for that covers this area is almost 100 kilometers away, we can still see this pattern from 2015 when an enormous number of birds were attracted to the beam. At about little after 10 o'clock on September 15th, you can see in the left-hand image where the tribute in light is that there's relatively uniform migration happening. In the next 20 minutes, a large pulse of birds arrives, and the area where that intense red is an increase in 2 orders of magnitude. So we go from basically a few hundred birds to suddenly 15 to 20,000 birds over the course of 20 minutes, and we can detect this on radar. This was an amazing opportunity to do some studies at the site when we realized that we could not only study this visually, but also see it with some of the quantifiable tools using radar and other means. it opened up a very powerful opportunity to study what was happening at the tribute. And I also want to highlight this amazing feature that I'll talk about more in detail. So that first image, that first video I showed to you was a typical video camera. It's actually taken on an iPhone. This is actually a video taken with a thermal camera. Okay, so this has, you don't see any of the tribute and light, of course, any of those bright lights. You just see the thermal response from the birds that are flying around up there. And what I want to highlight is what happens as the lights turn out. So you'll see a few hundred birds here. This is a window when we ask them to turn the lights off. And as we advance it just about a minute, you start to see fewer and fewer birds. We go another minute, even fewer. And when you finally get to the end, you see extremely few. The ability to impact bird migration in a positive way by turning off lights is almost instantaneous. Within 3 minutes of turning the lights off, almost all of the birds are returning to more typical migratory behaviors. And this is something that we saw incredibly well when we started to employ the different technologies that we could. Look at the right-hand image here first. You don't need to see the detail so much because you can see in green the period when the lights are on and in gray when the lights are off. You'll notice a periodicity of all of the different things that we're sampling. We're sampling the numbers of birds in the top graph, the speed that the birds are moving in the middle, and the vocal activity from acoustic monitoring in the bottom. And there's an incredible periodicity to all of those things when the lights are on and off that exemplifies exactly what I was talking about. There is a dramatic response when the lights are on. Birds increase in number dramatically. They slow their speeds because they're circling. The flight calling, the vocalization that birds use to stay in communication when they're migrating, it incredibly skyrockets during periods of lights when birds are disoriented and vocalizing more and more. As soon as you turn the lights off, the numbers of birds decline immediately. The speeds pick up because birds are flying in a single direction away from the beam, and the calling goes to almost zero, indicating reorientation and the lack of disorientation. So absolutely amazing. So we can see that these bright exterior lights, these kinds of installations have dramatic impacts. And if we turn those lights off, the impacts are almost immediate in the positive sense in terms of birds returning to natural migratory behaviors. Now, on the left, this is particularly relevant to what we saw in Chicago last night and early this morning. This comes from a study that was published a couple of years ago that highlights not only are the outdoor lights important in terms of turning those off to impact bird migration and bird behavior in a positive way, lights that shine through from the inside, interior lights, that is also a critical component. Turning those lights off, if we were to do so from a data set that spans 20 years in Chicago, if all the lights were off in this particular building, the same building, by the way, that killed over 1,000 birds last night with all the lights on, if the lights were off, we could have reduced mortality by 50%. And of course, with all the lights on, it would have been an enormous increase, which is exactly what we saw last night. So what I want to highlight here is that turning off lights can be a very, very rapid way of returning birds to more typical migratory behaviors. And it can be done inside and outside to dramatic impacts, interior and exterior light. So how do we relate the BirdCast work and some of the work we've learned about all these, the big data and the machine learning back to this kind of a approach where, oh, well, if we could employ the forecasts to tell urban areas or building owners and managers or homeowners, in the coming nights, there are going to be significant migratory movements, high intensity migration. Turn your lights off, please. We could potentially have really dramatic impacts. This is an example of some of those alerts. And these alerts that are based on the forecast model basically just set a threshold of high intensity migration. And when we achieve that threshold, an alert goes out. So this idea of being able to take the machine learning and big data that we can get from the radar data, sensing bird migration at night, and relate it to potential conservation actions and compelling people to act and giving them information to act in a timely way is really valuable to us. And we think a really important opportunity. We can also look at it at kind of a broader scale. This was the lights out forecast for tonight, and it's based on where intense migration was forecast to occur in the continental US, the contiguous US tonight from that map I showed you earlier. This is a product that's served up by our partners at Colorado State University, the Aero Eco Lab there. And basically the idea is all of those places on the heat map where you saw intense migration forecast are places where we're issuing lights out alerts. So where it's very red here, that is one of those areas that if you can turn out your lights, anything non-essential, indoor and outdoor, you do it. What's an example of how effective this can be? We've been working on a pilot project in Texas. We chose Texas as the pilot because in another study that we published a few years ago, we highlighted from the top 125 most populous cities in the United States, those that are the highest ranking in terms of exposing the greatest number of birds to light pollution at night. And Texas has two of those in the top 10, Houston and Dallas. So we began working in Texas because of this, and also because of the enormous movement that happens in Texas every year. Every spring, about 1 out of every 3 birds migrates through Texas that's migrating in the US, and in the fall, about 1 out of every 4. So if we could have an impact there and actually use these kinds of forecast models to have a situation where Houston, which is incredibly brightly illuminated, actually buys into the program and turns out lights. This is not a sort of a rigged photograph. This is not something that's Photoshopped. This is actual change that we can affect. We can get people to buy into this, and we can do so amazingly without legislation. Of course, Texas is very different from the northeastern US when it comes to maybe developing legislation that's based on conservation, that's based on birds, but we can still get people to buy in to this kind of a pattern because we can sell such a compelling message about lights going out saves energy, it's better for human health, and oh yeah, it protects birds that are migrating at night in incredible ways. So to bring it into the Northeast a little bit, we can also take the data that are behind BirdCast, use them in testimony in city councils, and amazingly pass legislation for bird-friendly activities, bird-friendly designs, bird-friendly operations. In the case of New York City, the lights out bills that were before the city council about a year and a half ago, they passed unanimously that will require all non-essential outdoor lighting on city-owned and leased buildings to be turned off during periods from 11 p.m. to 6 a.m. And this is all based on advocacy by people like you, conservation groups like New York City Audubon, also the science that Cornell and the BirdCast Project and our partners provided in testimony. All of that went into passing this legislation and enacting it. So a potentially very powerful way, again, of connecting how can we take the science, how can we take this fascinating understanding of birds on the move and turn that into conservation actions, take the big data, take the machine learning approach, and get it into a place where we can act on the data, something actionable, some support for making decisions. So let me continue and move a little bit from the radar into that other aspect that I've wanted to touch on. I've mentioned it briefly, flight calling. So when we think about aeroecology and studying birds that are aloft, we're not only talking about radar data that tell us a lot about the numbers of birds, of course, but we're also talking about acoustic data, which is a wonderful way of identifying the birds that are up there. For those that have known about flight calls or have heard them or have studied them, it's a wonderful way because they are species specific of identifying what's happening at night. They're not great at quantifying the numbers of birds because of course, not all birds are vocal at night, and one call may not necessarily represent one bird, depending on how birds are migrating. But those that are vocal, we can identify. So it is the reliable way of telling us what the species are that are migrating. So in conjunction with radar, which is telling us the numbers and direction, speed, altitude, if we can start to leverage the acoustic data. For example, this array of warblers that migrates in the United States, the visual image of them, and of course then the spectrogram, the visual representation of their flight calls and frequency over time. There's information here that, again, if we could employ some machine learning and some big data analytics, to teach models how to recognize this could be an incredibly powerful way of contributing more information to that BirdCast radar approach that I've just been talking about. So now we can do that. Hopefully, many of you know about Merlin Photo ID and have used Merlin maybe to identify a bird photograph that you have or taken a picture on your phone and used it. Incredible computer vision, machine learning technology under the hood there that basically relates expert knowledge about what's in a particular photograph to a model that recognizes how to identify these birds, and then something that's served up to your phone. So increasingly, we've seen that grow in wonderful ways, people using it, while at the same time, we've grown another aspect of it, the sound ID. And the sound ID part is particularly compelling, I think, because it has now led from the migration perspective to the opportunity for us to actually build models, take those images and that information I showed you in the previous slide of all those warblers that have unique flight calls, and start to train models around that and have the potential of thinking about, wow, could we actually really on the fly create a monitoring network for species based on acoustic recognition across the US or in any particular place where we might deploy microphones? It's starting to become a reality. And just to highlight a little bit how this relationship sort of works and what we think about it, why we've been thinking about it. So a study published last year, we were interested in looking at sort of a pilot data set we'd collected in 2015 and thinking, well, how does the acoustic information that we can collect relate to migration as we see it on radar? So we took a radar, the Binghamton radar near Ithaca, New York, near the Cornell lab, and characterized bird migration from that radar. We also did the same thing based on acoustics, and we saw this incredible overlap when it came to the peaks, when peaks were occurring, the intensity of those peaks, and this idea was born of, wow, there is real power in thinking about integrating these data sets because of the information that they both capture that's really kind of unique. And additionally, I want to call another element of this to your attention. So when we think about acoustics, obviously, and we think about species identifications and characterizing what birds are migrating at night, well, we may have the thought, well, why wouldn't we relate that to what we see on the ground during the day and the phenology, the timing of migration that we see from something like the eBird data? Again, all those observations that you all are submitting, how do those line up with the acoustic data? What we're recording at night, the species we're recording, with the birds that we're observing during the day, and the relative timing of movements that we see, say, in the northeastern US. And incredibly, right where we want to see this, that there's a close to one-to-one match. It's not perfect, but there's this one-to-one match along the diagonal there, that the patterns that we see, the timing of migration, the timing of peak that we detect for species, this array of species using acoustic methods, mirrors what we see in the eBird data. So both of these signs, the radar analysis and the acoustic, the eBird analysis with the acoustic data, highlight what we think is a really powerful future going forward for employing acoustics to add a whole complementary level of information to those BirdCast forecast and the dashboard data. Now, let me switch gears a little bit and get into some of the birding side before I close. I have a couple more slides to share. So what you're seeing here is an individual radar. And for the real hardcore birders in the group, that I hope a lot of you are, you maybe are interested in thinking about, well, when a hurricane or a tropical system comes through your area, you know it brings interesting things. It may transport seabirds from far, far afield. It may create fallout situations or concentrations of shorebirds and Jaegers and all sorts of things. Hopefully, you've had the good fortune to perhaps experience one of these amazing events. We've started to look at these sorts of events on radar and to try to understand, well, why are we seeing some of the patterns that we do? This was Hurricane Hillary that came ashore in northern Baja California and the San Diego area, maybe about a month ago, a little over a month ago. And one of the cool things that we're able to see on radar is these interesting patterns of, well, where are the birds in the storm? And there's a lot going on in these slides in this animation, but there's one very simple way to see what's happening. I call your attention to the bottom right quadrant. This is a product that the radar produces called correlation coefficient. I don't need to go into too much detail other than to say, basically, it's how sort of elongate or how spherical or how flat is the object that the radar is detecting. The flatter the object and the more elongated it is, the more likely it is to be a bird. The more spherical it is, the more likely it is to be some kind of a large raindrop. So what we're seeing in all those places in the bottom right where you see blue, those are all the places where the radar is detecting birds and biological scatter that's coming in with this inbound hurricane, okay, over the Yuma radar. And all the places where you see bright red and real intense colors, that's all precipitation. So this idea that some of us have been starting to understand over the last maybe 10 to 15 years, that most of the load of birds that arrives with a tropical cyclone of any kind is on the eastern side of the storm. We can now start to understand that pattern by looking at the radar data and how it characterizes where that biology is happening in the storm. And as it turns out, with this storm in particular, a lot of that biology was least storm petrel, wedge-rumped storm petrel, all sorts of, sort of amazing windfalls of storm petrels as far as Lake Havasu, obviously in the desert in parts of San Diego County, this incredible literal windfall of birds that arrived that we can start now to think about, well, why did we see the distribution of birds that we did? We can use the radar data to tell us some information about that. We can also do the same thing when we look at Hurricane Lee. Okay, so Hurricane Lee just came ashore in Nova Scotia several weeks ago. And again, I'll call your attention to that bottom right panel, and in particular, the place where you see the blue areas. Right. So that again is the biology, the bird dominated biology that the radar is detecting. Again, this is the east side of the storm. And the interesting thing about this storm, as maybe you've heard, so as Lee passed its way through the Canadian Maritimes and then eventually found its way across the North Atlantic into the UK, there was an incredible deposit of Western Hemisphere migrants, all of these neotropical migrants in the UK that were all associated with the circulation of Lee. And seeing these blues, these patterns, the biology inside the storm gives you a sense of how these storms wrap up or entrain these kind of migrants and can transport them really long distances. It's not just seabirds that get transported by these storms. It is also land birds as well. And there are some incredible cases of really large numbers of birds getting transported across the ocean. In 2005, Hurricane Wilma, very strong storm, transported hundreds, if not thousands, of chimney swifts from the Western Hemisphere or from North America to Europe. So they can be spectacular transport mechanisms for birds to move incredibly long distances. I also want to talk one more time about Lee and showcase what's happening from another perspective when we think about hurricanes. So this is a slightly different perspective. So what you're seeing here is the Portland radar as Hurricane Lee approaches. And you're seeing a pretty striking pattern in all of these images. So let me walk through what these four panels are. Top left, reflectivity, how much stuff is up in the atmosphere. Top right, the speed and direction of that those things are moving. Bottom left is a classification algorithm where the gray stuff you see is biology, all the other stuff is meteorology. And then that bottom right panel, that correlation coefficient, where the blue is representing the birds. And so you're seeing quite an incredible migration of birds over land, over Portland, and over that part of Maine as Hurricane Lee is approaching. Of course, as we know, as a hurricane's approaching, we think about its circulation. The winds are very favorable when a hurricane's approaching and you're off to this northwest quadrant of it for birds to migrate. And over land, there's incredible migration happening. But as the storm approaches in this animation, you start to see that migration contract tremendously. You see it shut down. And then eventually, as the storm arrives, it shuts down to almost nothing. Yes, there are still some birds migrating, but the idea of birds taking advantage of the incredibly powerful winds that are sort of farther afield in the bands of the hurricane, that are in the clear side of the hurricane where there isn't precipitation, as it's starting to move ashore on the west side, and these incredibly favorable conditions are happening, birds are moving at incredible high speeds. Some of these birds are traveling at 50, 60, 70, 80, even 100 miles an hour. So they're taking advantage of these incredibly favorable winds, and they're moving in advance of the storm. Of course, when the storm arrives, shuts down migration totally. Just another way to think about what it means for these storms and how birds actually can use them to their advantage when they're on the right side of the storm, so to speak, to migrate. So let me start to wind down here with the idea that we have this incredible opportunity to study migration from the perspective of all of these great tools that we have now. Mostly I've talked about the current generation of weather radar. But at the beginning of the talk, I mentioned the first generation, the WSR 57, the network that was here before the current digital network, the one that collected data on film. So amazingly, we have an opportunity now to go back to those data. There are still records of film canisters of all of those 35 and 16 millimeter films that took camera photos of the radar imagery that you see in the middle here and produced images like this. So on the left, you see a hurricane coming into Galveston, the early 60s. In the middle, that's actually one of Sid Gotro's images showing bird migration on the Galveston radar. And then on the right, you see a radar operator looking at the radar screen, making measurements. The cameras focus on that screen and photograph what's going on. And that's how the information that you see on the radar screens on the left and center were documented. So now, when we start to think about being able to study bird migration from that period, from the 1990s, back to the 1950s, if we could digitize all of those analog data on film and start to do things like this in a machine learning way, using computer vision and using some advanced modeling to identify these patterns the same way we do with the digital data of what's birds, what's meteorology, suddenly we have a treasure trove of information about bird migration that extends our knowledge back 40 years. And interestingly, there's a nice Philadelphia connection to this too. George Blood, who is one of the excellent digitizers and creator of archival information for the Macaulay Library, for the Internet Archive, for all sorts of different projects, is working on this and is slowly digitizing these films so that we can then analyze and expand our knowledge back 40 more years into the past of patterns of migration, of the intensity, of where it was occurring, and hopefully a little bit about how it's changed. It's not going to be the same information that we have available to us today, but there are enough places where there were operational WSR 57s at the same time there were the next generation WSR 88Ds operating, that we think there's going to be an ability to crosstalk and really extend our knowledge. So a very cool happening that hopefully I'll be able to talk about in another couple of years when we get through these data. And I should mention, there's a unique story about these data, that the original films that the National Climatic Data Center was holding were given to Sid Gotro maybe in 2000, very early 2000s. They were given to him because at that time, there was a sort of decommissioning of data that happened every 40 to 50 years. Data that were live and were available and people could extract and look at microfiche and look at films and so on. After about 50 years, National Climatic Data Center said, okay, we're going to deep store a lot of this, and the duplicate copies we're going to make available to researchers that want them. So they made those available to Sid. He took them. And as it turns out, not only did he take them, but instead of digitizing, instead of deep sixing sort of and deep storing the data, NCDC actually destroyed the films. So there was only one copy left. And it turned out that one copy was in an attic in South Carolina that was certainly not immune to king tides and flooding and hurricanes and wasps and rodents and all kinds of things. But amazingly, the archive survived. So we extracted it. I went down to visit Sid. We grabbed it and we brought it up to Philadelphia. Quite the adventure. And now we have this amazing opportunity to digitize these data and go backwards in time, hopefully. So why are we doing all this? Let me just sort of summarize with a very simple graphic here. You've all seen this, I hope. If you haven't seen it, you've probably unfortunately experienced it. Over the last 50 years, incredible population declines, in particular for migratory birds. And we want to reverse those declines. It's time to stop this process of pulling birds out of the system and killing birds. We want to build those populations back up. So part of building them back up is understanding and characterizing where are birds on the move, what kinds of hazards are they facing, what are the important habitats they're occupying, when are they moving, all of this kinds of information that we can of which we can avail ourselves with radar technology and other advanced technologies that we can use now to give us information that hopefully inform this critical conservation mission. And that at the core is the reason that BirdCast exists. Yes, we want to showcase the spectacle of migration. Yes, it is absolutely fascinating and a wonderful way to draw people in to understand that may not know anything about migration, how incredible this spectacle is. But of course, the bottom line is we want this spectacle to go on forever. So the idea of being able to take this science and capture the imagination of people, capture the information that's embodied in the tools that we can have and what birds are doing, and then turn that into information that can compel us to act and act in ways that are reasonable, that we can understand, that we can define. That is what's at the core of bird migration monitoring going forward into the 21st century. So with that, I think I've probably wasted a lot of my breath and a lot of time to the point that my voice is hoarse. So I want to open it up to questions. And before I do that, I just want to thank you all for listening and for the audience that you've given me tonight. And I also want to thank you or thank an enormous array of partners that are involved. This is not my work and my work alone. There are many partners involved. I mentioned they span a number of universities. They also span a number of on-the-ground partners. And the funding behind this comes from a really diverse array, including support from Amazon, support from the Leon Levy Foundation and Eamon Carter Foundation, National Science Foundation, of course, and also Lyda Hill Philanthropies. And of course, the information that all of you are submitting to eBird is also critical to this. So there's an incredible community and citizen science element to the work that we do. So thank you for that. And thank you for listening again.